Hi everyone, in this video we're going to be discussing some of the aspects involved in designing experiments. Some of those will be including comparison, blinding and the placebo effect, random assignment, and control and replication. Alright, let's get started. Suppose we want to design an experiment to see if caffeine affects pulse rate. So here's just an initial plan. We would measure the initial pulse rate, give each student some caffeine, wait for a specified time, measure the final pulse rate, and then compare the final and initial pulse rates. Sounds good to me. I mean, it's an experiment. I am applying a treatment here. What are some problems with this? Pause this video and jot a couple down. We're going to discuss your answers in class the next time we are together. So pause this video and answer these two questions. What are some of the problems, and what are some other variables that are likely to be sources of variability? In experiments, good designs are essential, right? If we want the experiments to be effective, just as they are for sampling. To see why, let's start with an example of a bad experimental design. So this is kind of what I explained in the caffeine one that I just posed. We start with our units, we apply a treatment, and then we measure a response. Unfortunately for us, outside of the lab, badly designed experiments often yield worthless results because of this idea of confounding. What's the remedy? Well, we're going to do a comparative example with two or more groups. Now, oftentimes you might have a control group. In an experiment, a control group is used to provide a baseline for comparing the effects of other treatments. Depending on the purpose of the experiment, a control group may be given an inactive treatment, which we cite as the placebo. Maybe they're given an active treatment, or maybe they're given no treatment at all. In all other aspects, the treatment group should still be treated exactly the same, so that the only difference is the treatments. Why do we need this control group? Well, if there's going to be convincing evidence of a difference in the average responses, then we're going to be able to safely conclude that it was caused by the treatments and not something else. Let's do an example. A group of AP biology students randomly assigned 100 corn seeds to be planted either at a depth of 1.5 inches or a depth of 3 inches. Explain why it was not necessary to include a control group of seeds that were not planted in the soil. So pause, think about this for a second. The purpose of a control group is to provide a baseline so that the results of a treatment can be compared. In this experiment, there is no need for a control group because the treatments just can be compared. The AP biology students are interested in knowing which treatment is more effective when compared to the other treatment. So a control group isn't going to be necessary there. Sometimes your control group, like I said, could be also receiving a treatment, but maybe if you're like a drug manufacturer and you want to know, is your new drug more effective than your old one, the control group would be giving the old drug, and then the treatment could be your new one. The placebo effect. The placebo effect describes the fact that some subjects in an experiment will respond favorably to any treatment, even in an active treatment. How often, right, if you are like, man, I really have a headache, and then you take something for it, and within minutes you're like, oh man, my head feels so much better. Do you really think the medicine has already kicked in that quickly, or maybe do you just think the medicine has, and therefore you think you feel better? The placebo effect is very real. Let's talk about double blind and blind, single blind. So in a double blind experiment, neither the subjects nor those who interact with them and measure the response variable know which treatment a subject received. So for example, if you were working with, I don't know, in a drug clinical trial, right? I'm thinking about like hospitals here. Both the doctor doing the trial as well as the subject receiving the treatment wouldn't know what they're getting, whether it's the treatment or a placebo or something else. Whereas in a single blind experiment, either the subjects don't know which treatment they're receiving, or the people who interact with them and measure the response variable don't know which subjects are receiving which treatment. Ideally, you'd love to do double blind. Not always possible, so sometimes single blind is going to be the way to go. You really need it to be at least single blind because, if the person knows like, oh, I'm getting the placebo, versus I'm getting a treatment, it's going to affect the results. Here's another example. W.H.R. Rivers is credited with creating the first double-blind experiment in 1907, just a little over 100 years ago. Rivers was interested in finding out if caffeine has an effect on work output. He quickly discovered the psychological effect on subjects who knew they were receiving a treatment. This led him to create a placebo for each experiment, which looked and tasted just like the caffeine treatment. Rivers would have a friend prepare the caffeine drinks and the placebo drinks and would then give the drinks to the subjects. We want to explain what it means for this experiment to be double-blind, and also why was it important for this experiment to be double-blind. Well, in order for this to be double-blind, that means that the subjects, nor the researcher, Rivers, knew which subjects were being given the caffeine drink and which subjects were being given the placebo drink. So it was double-blind. Neither the person running it or the people getting it knew what they were getting. Now, why is it important for this experiment to be double-blind? If the subjects knew they were drinking caffeine, Rivers wouldn't be able to determine whether any improvements in the work output was due to the caffeine or to the subject's expectation of working harder, right, like the placebo effect. If Rivers knew which subjects received which treatments, he might have treated one group of subjects differently from the other group. So then this would make it difficult to know if the caffeine was the cause of any improvement in work output. So this way, no one was able to really mess with it by their knowledge. Another important aspect in designing experiments is going to be random assignment. Now, this is not random sampling. We're not sampling. This is not an observational study. We're not doing a survey. This is random assignment, so it is different. In an experiment, random assignment means that experimental units are assigned to treatments using a chance process. Why would we want to do this? Well, the purpose is to create roughly equivalent groups at the beginning of an experiment, and so we would use this random assignment to determine which units get which treatment. Just a note, when you are describing how to do random assignment, don't stop after creating the groups. Make sure to identify then which group gets which treatment. There's lots of ways to do random assignment. You can use kind of all the strategies we use for simple random sample. You can use slips of paper, you can use technology, right, random number generator, or you can use a random digit table like Table D from our book. So let's go through an example and talk about how we would do this. So here's the question. Do students learn geometry better from an online course or in class with a teacher? To find out, a large high school set up an experiment with 500 student volunteers. It's okay that the students were volunteers here because we're not doing sampling, we're doing an experiment. So it's okay if they're volunteers because the random assignment is going to take care of the volunteer aspect. So the school randomly assigned half the students to take the course online, watching videos. The other half took a more traditional course with lectures by a teacher. We want to describe how you would randomly assign 500 students to each of the two treatments. So it'd be nice to have them be equal-sized groups. It's not always exactly necessary, but it does help. So if I have 500 students, I would want 250 for each treatment. So we want to talk how would we do with slips of paper, how do we do it with technology, and how do we use Table D. So here are the options. As opposed to being like, all right, let me write everyone's name on a piece of paper, and then, I pick you, and then I say, oh, you're in this group versus this group. Just on 250 slips of paper, write the word online, and on the remaining 250, write teacher. Okay? Shuffle the slips of paper, hand out one slip of paper to each student. Students who get an online slip will take the online geometry course, and students who get a teacher slip will take the course taught by the classroom teacher. Okay? This isn't going to be describing the full experiment. If you wanted to go further, you would then say, have them do this, and then, maybe see how they did on the final exam at the end and use that as their way to determine which one was better. How to determine the groups using technology. So you would want to label each student with a different integer from 1 to 500, and then randomly generate 250 different integers from 1 to 500. The students with these labels will take the online geometry course, and then the remaining 250 will take the geometry course taught by the classroom teacher. Once you have the first group, using technology. It's just whoever's left is in the second group. You don't need to like choose them again. They've already been chosen. And then finally, using table D, if you were given like a table or, random digits table, you have to carry this out. So you would, again, label each student with a different integer, but this time you need to be specific, 001 to 500. You would go to, any given line of table D, and you would read 3-digit groups moving from left to right. The first 250 different labels between 001 and 500, you would want to identify the 250 students who will take the online course. The remaining 250 will take it taught by the teacher. Ignore any digits that are outside of your range. Okay, so those are my 3 ways that I can do random assignment and with picking the groups. Let's talk a little bit more about control. We talked about a control group, but let's talk more about control in general. So in an experiment, control means keeping other variables constant for all experimental units. The purpose of this is to reduce the variability in the response variable, making it easier to identify when a significant difference is present. So for the variables that we do not have control over, we use the random assignment to balance the effects of this. Okay? So if you have no control over one aspect, you're hoping that the fact that you randomly assign them to groups is going to make up for the fact that you didn't have the ability to control this thing. We can't say that any difference in average response between 2 treatment groups must be caused by the treatments, because there would likely be some difference just because the random assignment is unlikely to produce 2 groups that are exactly equivalent. Okay, so this is a very important topic right here. And then lastly we're going to discuss is replication. Now, replication might not mean what you think it means. In an experiment, replication means using enough experimental units to distinguish a difference in the effects of the treatments from chance variation due to the random assignment. So, why do we do this? Because it decreases the impact of random variation on the experimental results, and it increases our ability to distinguish the effects of the treatment. Okay, so you wouldn't want to do an experiment with like 5 people and say, yep, this is great, like, here are the results. Because I did an experiment, I can do cause and effect. Well, maybe it was just because of, like, random variation, right? But if I would be like, well, I did this experiment with 500 people, and this is the results that I saw, then it's like, oh, okay, like, I can really see this is because of the treatment that I saw these results, and not just because of this random variation, chance variation, because of the small group of people. Like I said, here's a caution. In statistics, replications means using enough subjects, right? It doesn't mean doing the experiment again. It means using enough subjects. So here are our basic principles for designing experiments. The first one, comparison, right? Using a design that compares 2 or more treatments. This is where like a control group can kind of come in handy. Random assignment. So using chance to assign experimental units to the treatments. This creates roughly equivalent groups by balancing the effects of other variables among the treatment groups. Control. This is keeping other variables the same for all the groups, especially variables that are likely to affect the response variable. So if you were doing, the caffeine example, right? You would want to make sure, okay, everyone's drinking the exact same amount of caffeine at the exact same time, everyone's waiting the same amount of time to take their pulse rate, etc. Like trying to control things that you can control. This helps avoid any confounding variables, and it also reduces your variability. And then lastly is going to be our replication, right? Using enough experimental units in each group so that any differences in the effects of the treatments can be distinguished from chance differences between the groups. This is a lot of words, y'all. You're going to need to make sure that you can identify what these 4 principles are, what they are, and then why do we do them? Like, what is their purpose? So like, yeah, we need random assignment, but why? Yeah, we want replication, but why? So make sure you're really focused on that. In our next video, we're going to do an example of talking about how we see these principles in an example.